Good. Okay, hi, good evening. My name is Anreza binti Ahmad Samri and my team members, Dinesh Vijayan and Saurabh Akib. Today, we are going to present about factory robot farm. Our table of contents is, for the first one is introduction, and then problem statement, objective, methodology, result and discussion, and also demo. Before the introduction, robots became famous as a result of the efforts of Joseph Engelberger, known as the father of robotics. And robots can be used for various aspects of fulfillment, for example, in the warehouse industry. This is because robots are now being created and paired with AI or artificial intelligence, as well as machine learning. And the data again from such sensors as visual and auditory sensors, warehouse robots can be equipped with thermal and haptic sensors as well. Okay, then Saurabh will explain about the problem statement.
All right, thank you, Anna. I'll talk about the problem statement. So we based our model of our robot basing on 3 problems that we could think about. So there are limited human capabilities, increase in wage and energy, and human negligence. So let me talk a bit about them. So for the limited human capabilities, humans are, okay, so our factory-made robot. So what we thought about is humans are unable to lift heavy objects and are easily bored to repeat the same job. So a robot can actually be programmed to do the same work over and over again, unless or until it has some overheating issues. And if we use the right materials, we can we can allow our robots to perform heavy tasks as well. Then increase in wage and energy. We all know that for human manpower and for human work, human has a limited manpower, and over the years, it will actually increase a factory's cost. If we replace humans by robots, we can actually decrease. A factory can actually decrease their cost over a long period of time, as well as employees need to pay higher salary as well as recruitment. So a robot actually solves all of these problems. Okay. Thirdly, we have human negligence. Sometimes people are careless and managing things. For example, dropping things and causing losses. We're not going to say that the robots are going to be absolutely perfect and their work will be flawless and there'll be no mistakes, but the probability for a robot to make an error while performing a task or performing a set task is much less than a human, because robots are directly programmed to that. Can you move to the next slide? All right, so now we'll talk about the objectives. So we had 2 objectives in our mind. One is to produce a robot arm that can be used in a warehouse to facilitate lifting and placing items in the right place. So what we focus is to implement our robot at a manufacturing factory. So it is a very simple robot, and we just assume that it will pick up from a particular position, lift it up, and then drop it off at another particular position. And our second objective is to build a robot arm that is a physical representation of the fundamental of kinematics. So to implement our robot successfully, we try to implement the fundamentals of kinematics. So we can determine at the pinpoint location of where the object needs to be lifted and where the object needs to be dropped. So our tasks can be carried out successfully without any hassle. All right. So next, I would like to ask Dinesh to talk about the methodology.
Dinesh, you were mute.
Okay, sorry. So for now, the methodology, obviously we want to implement what we have learned in robotics class, which is kinematics. Well, in this case, in this problem, we are looking at the inverse kinematics. So about the method, basic overview is we want the robot to move to a point of X and Y. That means if we want the robot to pick up the ball, it needs to go to the particular ball's position. Hence, we need to do the inverse kinematics to understand how much angle shall the robot move. That means the arms, the end effector, and also the revolute joint. So this robot, we assume, consists of 2 degrees of freedom, which is the base, the revolute joint, and lastly, the end effector, which is the part that will grab the ball. Next. So first we do a planning. So you can see in the brief image down there. So we make an assumption of how to solve this problem. So let's say the ball is at position P, 4, 1, X4 and Y1. Conveyor belt is at a point P, 3, 3. And the length of the arm, L1 and L2 is both 3. So next. So since we have all the particular variables, we can now move on to inverse kinematics. For the end effector to reach the ball, the first hand needs to move an angle of θ1, and the second hand needs to move an angle of θ2. As you can see in the image, the θ1 and θ2 is there. Since we have all the values, we can use inverse kinematics to find the angles. Next. Okay, so here's a proposed solution. So using trigonometry and cosine law, we can solve this problem to find the angles. So you can see in the image there is a small write-up on the solution, assuming that the ball is at position 4, 1, the length is 3, 3, and how do we get there? We need to find θ1 and θ2. So to find θ2, we use the cosine law, as we learned in class. And then to find θ1, we basically draw a big triangle, and then we find it using trigonometry. So with these values calculated, the end effector can reach the ball. So this is the basic fundamental of how the robot should work in the X and Y plane. Obviously, it's a 3D robot. It needs to have an X, Y, and Z plane, but we implement what we have learned so far on the X and Y plane to see how inverse kinematics can be used on this robot. So next, so this process can also be used to calculate the angle to go to the conveyor belt, similar process. Next. So before the demo, what obviously we use is we use a tool called VBot. So to apply our calculations programmatically and to visualize the simulation of the robot, we have chosen to use VBot. So why? Because these two consist of the libraries for programming of movement, simulation to visualize the robot movement, and ability to write own program for the robot. So next. Okay, so the result discussion. So basically in this experiment, we were successful to design the robot. The experiment was, the obstacle was overcome through the understanding of inverse kinematics. So the robot managed to put the ball, pick up the ball and put it on the conveyor belt. So that was the target. So next. So the limitation, like what I mentioned earlier, is the X and Y and Z plane. However, we can make it better, obviously, if we add camera, depth sensor to judge the size of the ball. And then next, the robot should also be programmed to determine the weight of the obstacle being lifted so it does not carry more than its capability. Next. Okay, let me pass to Anna for the demo of our robot.
Okay, let me stop share this slide first. Okay, like Dinesh mentioned that we are using VBot. So first I need to refresh this first. Wait, Okay, for this robot, we only cover for the kinematic robot arm, which is this part where we have a base and then the revolute angle and also the end factor, where the robot will pick up the item and then you will move maybe about the 90 degree to put the item back onto the conveyor belt. And then for this part, we didn't cover this part for the sensor part. So let's like we mentioned in the limitation where we have the limitation on sensor and that we can improve in the future work. Yeah. For this part, it's only for the robot to pick up the item and then put in the item into the conveyor belt. Next, you want to add more? Anything?
Yeah, like what I mentioned earlier, the reason why I choose Weebot is because there's as you can see the code, there is a lot of libraries to help us code and do the major calculations needed. Yeah. So that's all, I guess, for the demo.
Okay.
I think that's all for our presentation. Anyone want to add anything?
Yeah, that's all.
That's all right.
Yeah, that's all.
Okay, thank you. Okay, I think you can stop the recording already.